Okay, we should get started. So the class on Monday was interrupted by the fire alarm, you remember, and there's a little bit of material we've still got left to finish on the IIR filters. I was thinking about trying to edit out a video and send it to you, but I think we can just cover it right now, and then we'll move on to FIR filter design. So let's get started. So we went through this process of learning how to design analog domain filters, the Butterworth, Chebyshev, elliptical filters. And we had these techniques, these polynomials that have this nice property of having equal-sized ripples in their magnitude responses, which, because when you push down a ripple somewhere, it's going to pop up somewhere else, sort of intuitively. If we can make all the ripples the same depth, then that's what we're looking for. That's going to optimize the largest depth of any ripple, right? It isn't. We're balancing them all, so we can't reduce any of them without increasing the overall bound. That very often that's the criteria we want to achieve in practice with these kinds of filters. We say, okay, we've got a limit on how close we're going to get to our response. We'll design a filter that'll just touch that limit, and it'll do it multiple times. And so once we have that constraint, then these are the polynomials that give those responses, give these equal-sized ripple responses. So they're the kind of the ideal solution to these things. And so when we try and actually build these discrete time filters, we want to use those same polynomials, but they can't be exactly the same, because instead of trying to get the frequency response on the imaginary axis, we're now trying to get it on the unit circle. So we construct this mapping between the S-plane and the Z-plane, such that if we have this polynomial on the S-plane, defined by a set of poles and perhaps zeros, that gives a particular set of values on the imaginary axis, we're going to get the poles and zeros now placed on the Z-plane, such that we get those same values on the frequency axis in the Z-plane, that is the unit circle. And so the bilinear transform is this mapping between these two planes. It's this one-to-one mapping, but this fairly weird, mind-bending mapping that manages to move the whole plane around, although maybe it's not that impossible to understand if you remember that little video about the sphere with the light projecting through the points on the surface of the sphere. Okay, so we can do that, and then when we do that, we end up with this relationship between the continuous time frequency values and the discrete time frequency values, which has to be a mapping of an infinite frequency axis in continuous time onto a finite range of frequencies in discrete times. Actually, as we noted last time, it's a periodically repeating finite range, but the principal values are between, in discrete time we can only have the radians per sample vary from -pi to +pi before we start getting aliasing, we get repetition. But we're going to map the entire -infinity to +infinity radians per second continuous time frequency axis onto that thing, which we do with this arctan function, which has these asymptotes, so that the infinite range of big omega falls into a finite range of little omega. That's okay. And then if we want to know what's actually going to happen to a particular analog filter, which has some magnitude or frequency, magnitude and phase response as a function of big omega in the analog realization, if we put it through this mapping, all we do is substitute for S with this, whatever it is, 1 minus Z on 1 plus Z. And we get a new polynomial in Z, which is going to have a frequency response. And every point on that frequency response will correspond to one point on the frequency response of the continuous time filter. And the particular point will be related by this mapping between little omega and big omega. So we can take this continuous time parent magnitude response, and then we just take every frequency feature here. We take the frequency, find the point on the curve here, project across here, and we get this corresponding point, the same dB level, the same phase at this new frequency in the discrete time frequency axis. And so, because it's a monotonic mapping, right? So low frequencies and high frequencies remain the same place relative to each other. So if we start off with a bandpass filter with a 20 dB stop band attenuation and a certain number of ripples, we're going to get a bandpass filter with a 20 dB stop band attenuation and a certain number of ripples. It's just that the actual frequencies will be warped, and they won't even be simply scaled. They're stretched and compressed in different ways. But basically now we can build a discrete time bandpass filter by designing a continuous time bandpass filter and then just making sure that the frequencies that we need in the discrete time are placed in the right place in continuous time, which is this idea of pre-warping. So we have specifications in the discrete time. We then put them through this mapping to map from the discrete time to the continuous time, design an analog filter with those continuous time frequency characteristics and then the same magnitude characteristics as we need in our final filter. And then when we apply the bilinear transform, we know that it's going to undo this. It's going to map these things back. So we'll end up with a discrete time filter that has the frequency points that we actually want. So we had this example here where we were trying to design a low-pass filter with ripples in the pass band and monotonic and stop band, so Chebyshev 1 filter with these particular frequency points, 0.4 and 0.5 pi radians per sample as the pass band edge and stop band edge in the discrete time domain. So then we just have to figure out what the continuous time pass band and stop band edges will be in our kind of notional, fictional continuous time domain, which we're just inventing just so that we can build a filter that will then do what we want when we map it back into discrete time. We get some values out here. We can build the filter, and then we can get from the values, we can figure out the filter order, then we can build it, and we can map it back. So here's just the shorthand, the quick way in MATLAB to do this. Given these calculations, which actually MATLAB will do for us as well, but given these calculations, we then just plug it into the Chebyshev 1 function. We get the S-domain polynomial out, and then MATLAB will do the algebra to convert that into, or do the, the expansion to convert that into a discrete time function just by doing the bilinear substitution. The 0.5 is just the scaling constant that we use by convention. So here are sort of the comparison of these two filters plotted in a way that makes them look very similar, right? So here's the continuous time filter, which I get from frec S of B, big B, and big A, which are the continuous time polynomial coefficients. And then here's discrete time frec Z of little b and little a, which came from the bilinear transform. And in both cases, we see it's this low-pass filter with ripples, a little bit of ripples in the pass band, and a nice monotonic fall off. The discrete time filter has this pass band edge at 0.4 pi radians per sample and this stop band edge at 0.5, though we can't easily see that, because that was how we designed it, right? That was what we were trying to achieve. That was our initial specification. And so we designed this continuous time filter to have a pass band edge at 0.72 or whatever, such that when we put it through the bilinear transform, it landed up where we needed it. These filters, at a glance, you might think, oh, it's the same frequency response, just, plotted on different axes. Of course, it's not that because of the warping of the frequency axis. So here I've just done the same thing. So here I just did what we saw on the slide. I took the, I designed a Chebyshev 1 filter, converted it in discrete time, the bilinear transform, and I just took frec S and frec Z to get the frequency response and frequency values, just the default ones that it generates for S domain and Z domain. Then I plotted them, and I plotted them here. I normalized the frequency axis for the analog filter so that it would also have the pass band edge at 0.4 pi. So that when we look at these two things, and if we link their axes with link axis, they have their edge at the same point here, which is it's 0.4 pi, right? 1.2 something. But of course, this one's now in radians per second and radians per sample. But this is lining them up to make them look as similar as possible. And they look pretty similar. We've got some ripples here, and we've got some slope here. But if I zoom out somewhat, like this, we see the difference now in how this slope falls off here. This is from 0 to pi radians per sample. And so this is like this is the asymptote of the frequency axis in discrete time. We can't, after this it starts repeating. And what happens for this Chebyshev 1 filter is that the gain actually goes to 0 at omega equals pi, which is to say that this monotonically decaying, and it gets shallower and shallower as time goes on. If you go to infinity in continuous time, the gain of this low-pass filter is 0. Of course, you'd never get there. But here, on discrete time, we actually do see that value at infinity. And we saw there were a bunch of zeros at z equal -1, corresponding to what happened when you got to the end of frequency on this plot. So here we can see that they look kind of similar up here, but they look very different over here. And this is the effect of the arctan warping function compressing all the points for these higher frequencies into this finite range. If we actually take the point where the gain is at -100 dB, those are the same sort of values of the polynomial. If we looked at the phase at those points, they'd be the same phase. But the frequencies have just been warped by this arctan function. Similarly, actually, if we zoom in on the passband detail in here, zoom in all the way so we can see the depth of the ripples. Okay. So here we see the specification was to have 1 dB ripple depth, and we've achieved that very nicely. Yeah.
The discrete frequency in the x-axis, is that
Yeah.
normalized to pi, or it's not?
No, this isn't. I didn't normalize it. So you saw that it went up to 3.1. Normally I plot it normalized by pi. I didn't. So it's actual radians per sample.
The response of that would be like from 3.14 to pi to 2 pi would be 0, and then from 2 pi onwards it repeats the same way.
Yeah.
Is that,
So I could actually plot that. So what happened? That's just. Okay. Let me just plot something here. So we got these frequency response values from FREC S. And FREC S, if you just pass it like this, it'll choose some range of frequencies that suits it. We don't really know what it's going to choose. I'm trying to think how to do this. And similarly with FREC Z, it'll either choose a range of frequencies which is 0 to pi normally, or you can tell it to choose a range of different frequencies. So we could say, go in steps of 0.01 to like 4 pi here. And then let's just plot those. WA 20 by log 10 abs HA. So that should plot that in dB. That's the analog thing. And so this is in radians per second, going up to 10 radians per second. It doesn't matter how far you can go, however far you want. Let's put a grid on that. But here we can do the same thing for the discrete time one. If we can, so 212, there you go. Okay. And so this is, if I link the axes of these ones. So in this region, this is the pass band, and we see again it's like ripply and has a nice little thing. I didn't scale the axes here, so they're not actually the same. They don't have the same pass band here, but whatever. You can sort of see that they have a similar shape over here. But here, for the continuous time one, we can go up to whatever frequency you like. It's going to keep going down. Here, for this discrete time one, now I plotted it not just up to pi, but up to some factor of pi, and we see that beyond pi it starts repeating, and so we get the whole thing. This is the alias around 2 pi here. It's the alias around 0, and then it goes down again, right? So that's clearly they look very different from that in that respect. But
so,
yeah.
Ideally, we want a filter which would attenuate a frequency not in the band of interest. Like say if I want like specific attenuation at a frequency, say at 3 pi by 4, 3 pi by 2.
Yeah.
I'm not getting that attenuation here because of this aliasing happening.
So at 3 pi by 2, that
Say
frequency?
something like after pi,
Yeah.
around something between 3.14 and 4.
Yeah. So I'm trying to build a low-pass filter, but you're pointing out that, well, this is not a very good low-pass filter because look at all these frequencies in here.
Somewhere in that band, I'm not getting an attenuation.
Yes.
That being additional.
You mean these values here, right?
Yes. I mean,
Yeah.
After 2 pi, I understand because it's
Oh, after
basically
2 pi?
It's periodic with respect to 2
Oh,
pi.
it's just these points in here?
Yes.
Yeah, well, these points in here are not... Okay, there's a... You know, I could have plotted over here, and I've got this symmetric passband, you know, for negative frequencies. And so let's not forget what negative frequencies mean. When we want to have... I mean, the reason we plot only between 0 and pi normally is because for a real-valued system, the frequency, the Fourier transform is going to be conjugate symmetric. And so the negative frequencies are going to have the same magnitude. They're just going to have the same magnitude and the negative of the phase. Because the periodicity, this chunk of frequencies here is going to show up here as well, leading up to 2 pi. So this response, this symmetric response, which is what it would look like if you plotted it around 0, that's, you know, you've got to have that if you want to have a real valued system. We could try and build a filter that had only let through positive frequencies and had 0 for negative frequencies, which would give us 0 values in here. But that would be a system that had a complex impulse response. Because the positive frequencies, you know, the positive frequencies correspond to, you know, these complex sinusoids, right, spirals. If we want to have just a real value thing, we've got to be able to add in the conjugate versions of those, which are the negative frequencies. That gives us a real sinusoid, and then by changing the actual relative phase of the real imaginary parts, we basically vary the phase of the sinusoid that we get when we get the real imaginary parts cancelling out.
But saying we need to add in the real values, I mean, the poles and zeros or the actual frequency points? Because
No, the actual frequency points. Well, in the time domain. So all I'm saying is that, you know, e to the j omega n plus e to the minus j omega n, right? This thing is cos j omega n plus cos omega n plus j sine omega n, right? That's just Euler's equation for that complex thing. And this one is cos omega n minus j sine omega n. So this thing is just 2 cos omega n, right? So in order to get a real cosine function of time, I need to have these two components, which of course are the Fourier transform of, you know, so if this is x of n, then x of e to the j omega is just going to be delta of, okay, let's call this omega 0 here. It's going to be delta of omega minus omega 0 plus delta of omega plus omega 0, right? So the point is this real sinusoid in the time domain, I can build it out of these two complex exponentials, and because of the way I define my Fourier transform in terms of complex exponentials, that means it has this Fourier transform which has got this nice structure, but the structure has both positive and negative frequencies, right? So this Fourier transform looks like these two deltas. So this is omega here, this is omega 0 here, and minus omega 0 here, because this one gives us an impulse of minus omega 0. So to generate any cosine, like any real function, we need to have both positive and negative frequency parts. If we'd want to get sine here, a different phase, then we would have ended up with different coefficients for these things, but the magnitude would still have been the same. Yeah.
I have a question. I can't see it.
Yeah, me either. Okay. What happened? Okay.
So, yeah, so I think similar to what he was saying, I don't know, but Yeah, I understand you need to conjugate like negative and positive
Yeah.
frequencies. But if I should interpret this, so you still have the positive half of the frequency response
Yeah.
shifted. So let's say I want to filter on an A440.
Yeah.
I don't want any of the octaves higher than A440.
Yeah.
So this is telling me that if I
Yeah.
have 2 octaves higher than A440, you're still going to have the same
Okay.
amplitude.
Yeah. Okay, great. Thank you. So that was the sort of the second half. The first half is like, well, what happened at these negative frequencies? And it's like, don't think that the frequency just means any sinusoid. The positive frequency means the positive going complex part, and so we need a negative part to cancel them out to make real parts. So we need both positive and negative frequencies. Then it's like, well, what happens about these higher frequencies? So what about this part? Like, I wanted to just have a low-pass filter, and you're telling me I'm getting all these frequencies coming through here. It's so much worse than that, right? That it's not like, oh, we can build this filter, we can have these frequencies coming here. What this means, right, is that this is all radians per sample, so it's relative to the actual sampling rate we're taking. These frequencies up here correspond to frequencies where if they were pure sinusoids, they'd be completing more than one half cycle every sampling interval, which basically means we've got a signal that we've got a sinusoid that looks something like this, but then we're taking samples where there's more than half a cycle of the sinusoid before we get to the next sample. And what we end up with is something that looks like an aliased, a lower frequency sinusoid, right? So yes, it's true. If I had this system and without any kind of anti-aliasing filter, I put in a frequency up here, even though that's a frequency that should be in my stop band, it's going to pass it pretty well because what will happen is that when it samples, it'll alias it down to make it appear. How come it's timing out so soon? I don't know. It's strange. It'll alias it down to make it appear like a frequency down here, and then that's now within the passband, and so it'll go through fine. But the problem is not in the design of the discrete time filter, because of course, if we want to have large gains in here, then we're obligated by the periodicity to have them every other place. The problem is in how we sample the original signal. That basically, before we even put this into the discrete time domain, we've got to take our continuous signal and make sure it is band limited to below, half the sampling rate, to below the Nyquist rate. Otherwise, we're going to get horrible stuff. But that's comes much earlier than the problem of the system itself. It's just because if we sample something that has energy above the Nyquist rate, then already that's been totally confounded with the actual part of the signal we care about, because we folded all those spectral components together. And so whatever we do, we're never going to be able to separate out the energy contributions at these aliased frequencies.
So you're saying we have to sample below the Nyquist rate?
We have to sample. The Nyquist rate is half the sampling rate. Okay, that's what that's what it means, at least for our purposes. We have to make sure that if we care about some frequencies, they're within our Nyquist range, right? So we're sampling at double the. We'll talk about more of this. And at the same time, when we actually do the sampling, when we run our A to D, we have to make sure that we've already eliminated any energy above that Nyquist rate from the analog signal. Otherwise, it's going to cause aliasing. That's what happens. Yeah.
So are we okay? So we have in the original signal, we're supposed to remove any high frequency components, like say from pi to 2pi, basically fs by 2 plus. But are we really concerned about high frequency components above 2pi? I mean above the sampling frequency fs? Because anyways, if we have a frequency component above the sampling rate, we cannot basically regenerate that in the digital domain. Right?
Absolutely.
We don't need to basically care about any frequency component higher than the sampling rate. Like say all the images greater than 2pi.
So assuming we're starting with some kind of real world signal that can have any kind of frequency components in it, we have to care about them in the sense that if we just pretend they're not there, then when we do our sampling, we're going to get aliasing and we're going to be in big trouble. So we have to remember that they could be there, meaning that we have to filter them out before we do our sampling, which is not. All the stuff we've talked about here, we've assumed that's been taken care of, but we will talk about it briefly again at the end of the semester. If we actually wanted to manipulate some of those frequencies, we're in a lot of trouble, right? Because basically we we'd need to use a higher sampling rate to be able to control those frequencies. If we're sampling at 8 kilohertz and we're trying to, select for some signal that's up above half of that, above 4 kilohertz or 8 kilohertz, 16 kilohertz, if we've done our anti-aliasing filter right, then it'll be filtered out before we even get into the discrete time domain. And if we haven't filtered them out in the anti-aliasing filter, then they're going to be aliased along with these baseband components, these components between 0 and 4K. So either we have to make sure that there's some reason why the aliases don't matter, or we're in trouble. So, so maybe this plot is a little bit confusing, but I guess it's important that we should remember that's what it's going to look like when we plot it like that. So basically, we can't control these things independently because they're just taking the values, going round the unit circle on the z-plane again and again and again. So they're going to repeat inevitably. But we can control these range of values. That's the filter design, and so that's what we do. That's how we're that's the game we're in. But even now, when we zoom in just to look at this part, which is now the part we always look at, the well-behaved part of the discrete time frequency response, we still see this difference between these two because essentially we've compressed everything into this. Okay, let me. I think it's very useful and important to have a little reminder that there is this, this relationship to continuous time that totally matters. It defines what makes, in what sense the discrete time system makes sense if we're relating it to continuous time. But this is not really what we're talking about right now. We assume that part's, that's always underlying any kind of discrete time system, is that we've got some connection to the continuous time. And so now we're just worrying about a discrete time setup. So getting back to this plot, which is where I plotted the two filters, and then I only plotted up to pi radians, and I'd sort of normalized the frequencies. Now we can zoom in on these pass bands, and we see that against little omega, we have this 1 dB deviation, which was the filter design, and we have 1, 2, 3, 4 peaks in our ripples. Here's the big omega radians per second, the pass band, which just because I can scale it, I've arbitrarily scaled it to have the same value, same numerical value here, even though it means something different. And again, we see 1, 2, 3, 4 peaks because the bilinear warping will map all of those features into the same part of the pass band. But notice that they're not the same points, right? They're a little more spread out. Well, this one's slightly higher, slightly higher, slightly higher. And yeah, so they're a little bit squeezed up in the discrete frequency axis, which is what you get from that arctan warping function. But if we did plot it against with the normalized frequency axis, so omega on pi. Let's get it back without the big range here. Okay. If we plot it now, this is radians per sample divided by pi. And so here is this passband edge that we tried to achieve. And lo and behold, right, it's at 0.4 pi is when it goes through minus 1 dB, which was the thing that we requested. And then we're also trying to control the gain at 0.5 pi, which I forget what we wanted it to be. We wanted it to be at least 40 dB at 0.5 pi. And so here it is, 0.5 pi, it's 40-something dB again, because we had to use you know, the ideal Chebyshev filter would have been 7.09. We had to go to 8th order, so we had extra order, so we got extra attenuation here when we worked that through. Okay, so that was kind of an interesting little diversion, but just to get to the point of like, what do we actually get when we do this bilinear transformation? We do get this filter, but it has these different frequency responses in the analog prototype, different frequency values in the analog prototype. Any questions? Any more questions about that? Okay. All right, so now we've seen how we can go from an analog filter design through to a discrete time IIR filter that has the same ripple characteristics, ripples in the passband or ripples in the stopband or both, and has passband and stopband edges that we can control by pre-warping and mapping to the analog domain. If we want to get a different kind of filter, so not a low pass, but say a high pass or something, we can basically do the same thing of mapping our requirements, our passband and stopband edge or edges, into continuous time, and then doing the transformation to get the discrete time filter, making sure the frequencies land up in the right place. So here this would be the overall design process. We have a specification in discrete time. We warp the frequencies to get the specification in continuous time, in this pseudo-continuous time with these notional equivalent frequencies. We do the design in the analog domain to get our prototype, our analog domain prototype, which is a low-pass prototype. And then, the normal thing we do if we wanted to design a high-pass filter in the analog domain, we'd have some transformation which takes a low-pass prototype, converts it into something like a high-pass or a band-pass. And then we could just plug in our bilinear transform, which would map us into our discrete time domain, undo this warping, and give us the filter that we needed. We do actually have an alternative, which is that we can go straight from this low-pass prototype in the continuous time. We can do bilinear transform here to get a low-pass prototype in discrete time. And then we can do this transformation to go from low-pass to some other form, like high-pass or band-pass, in discrete time. It's notionally the same process, that we have some way of mapping the frequency axis so that we can get the magnitude values to show up for a different range of frequencies, but it's an actual different kind of mapping. And so, why complicate things? We've sort of got this worked out. But the idea of generalizing this process of mapping using a substitution, a mapping of the entire z-plane to get a different kind of filter, it's interesting to see how we can do that in the discrete time domain, because there might be other situations where we actually want to do this transformation. So, okay, when we wanted to do the mapping, the bilinear mapping to get from the S-plane to the Z-plane, there were two things we had to do. We had to make sure the frequency axis mapped onto the frequency axis, and we had to make sure that the region for stable poles mapped onto the region for stable poles, so that the system would have the same frequency response or the same magnitude response values and would still be a stable system. If we do this completely within the Z-domain, we can do the same. We can try and do the same kind of thing. We can have this mapping to get a desired polynomial in Z, which is just the prototype low-pass polynomial in Z, where Z has been substituted by some function, where there's some one-to-one relationship between the Z variables, Z and Z hat. And the mapping, which is just the mapping of the Z-plane, should map the unit circle onto the unit circle, so that these magnitude response values that we've carefully designed remain the magnitude response values, or the frequency response values, magnitude M phase. And we want the unit circle interior to map onto the unit circle interior, so that the poles, the places where the polynomial goes to infinity, they still correspond to stable poles. So mapping the unit circle to itself means that for the magnitude of z hat equal to 1, we want the magnitude of f of z hat to be equal to 1. And mapping the interior of the unit circle to itself means that for magnitude z hat smaller than 1, so that's all the points in the inside of the unit circle, we want the magnitude of f of z hat to be smaller than 1. But what does this say? Here we're saying that we've got some function of z, a polynomial in z, and we're specifying what values it should take on for all the values of z whose magnitude is 1, which is the values on the unit circle. And we're saying that its magnitude should be constant, should be 1 and constant for all those values. That's actually an all-pass filter, right? If we just think of now, well, we've got some polynomial in z, which is like defining a system in the z domain, and we're specifying what its values should be for the unit circle, which is like specifying its magnitude response. And we're saying it should be constant, should be 1. But that would be an all-pass filter, a filter whose value on the unit circle always has a magnitude of 1. That means to say it's Fourier transform, the gain that it would apply to any sinusoid would be 1. And so that's all we need. It's just saying, well, we're looking for this f of z, which is this mapping that we can apply in the polynomial to get a new polynomial out. But that mapping is actually equivalent to an all-pass filter, which, wouldn't be that interesting, except that we already know how to build an all-pass filter. It's just a rational polynomial in z where the coefficients are mirror images of one another. In fact, what we've done is we've defined it sort of the backwards of the way we want to do it, but that's okay because it's fairly easy to inverse. It's still a mirror image polynomial. It's just that we replace the numerator and the denominator. And so, okay, so now we know how to do this substitution algebraically, right? We could build one of our all-pass filters, a plus bz to the minus 1 plus cz to the minus 2 divided by c plus bz to the minus 1 plus a z to the minus 2. We can substitute it in. We get a new polynomial out, which would have some mapping. But actually, you can actually do this directly in the implementation. If you think about the flow diagram that produces a filter, basically we have a bunch of gains and connections, and then we have these delays, these one-step delays, the z to the minus 1s. And it turns out that, basically we're defining this polynomial by working out this operation as a bunch of individual applications of z to the minus 1. So if we just take each of those delays and replace them by this all-pass filter structure, we end up building this discrete time warped filter. It's not that useful because the warps you do here are kind of limited, or typically quite limited. But it's kind of cool that you can do it, and it's just this nice way of tying together the block diagram representation with the actual z to the minus 1s, which is just like a notation, and saying, no, that really means something. It means that you can build the system out of delays, the delays z to the minus 1, and if we replace that z to the minus 1 delay with some equivalent mapping of the z-plane, then we also get a valid z polynomial. All right, well, I don't want to stress that too much, just sort of let you know that it's there. Of course, as with the bilinear transform, the key point about this transformation is well, where do those frequency points line up? We've mapped the frequency axis to the frequency axis, in this case the unit circle to the unit circle. But if I have a frequency, a particular gain at some frequency in my original filter, where does that gain land up? For which frequency does that gain land up in my mapped filter? And so, it depends on basically now the phase of the all-pass filter that you're using to replace the delays. If we have the simplest possible all-pass filter, first-order all-pass filter, so the polynomial is 1 alpha and then alpha 1, we can work out exactly what if z equals z hat equals e to the j omega hat, then the mapped version z equals f of z hat is going to be z hat mapped in here. We know that this thing is going to have a unit magnitude. That was kind of the point. But we can work it out. It's going to be some particular it's going to have some particular phase. It's going to be e to the j omega for some omega, and the relationship between omega and omega hat works out to be this. It's a relationship in the tangent domain, and then it depends on the alpha parameter here. So if alpha is 0, then it's a one-to-one mapping, because that's just a degenerate all-pass filter. But for other values of alpha, you get this sort of one-dimensional warping of the frequency axis. So you can take some kind of filter, an arbitrary filter that's got some shape on the discrete time axis, and you can squeeze those features up or down by replacing the delays with this first-order all-passes and then having different values of alpha in here. So you see that this is like our arctan warping function we had in bilinear, but now instead of mapping from infinity to pi, it's mapping from the range 0 to pi to the range 0 to pi, but it's just stretching the points around. So if I had some feature, some bandpass filter with a pass band at 0.6 pi, if I then replace the z's with this all-pass filter with an alpha of 0.6, I'm going to land up with that pass band now being around 0.9 pi radians per sample. Or if I did minus 0.6, they would land up at 0.2 radians per sample. And so that's this thing. You can give me any z-domain system, and I can just move its features around without, again, changing the actual magnitudes of the magnitudes and phases of the individual frequency response values, just the frequencies at which they occur, just by doing this substitution.
Doesn't that automatically change the phase as well? Like
Doesn't change the
phase
It doesn't change the phase response. It changes the group delay, right? So if I have a phase response which starts out looking like this, and then I put it through some warping function, so all these points get warped down, so it looks kind of like this, right? So it's a warping function that has this nice untight warp. The phase values are going to be the same. They're going to occur at different frequency. But the things that matter about the phase response, which is like the local slope, because that's the group delay of those frequencies, that's going to change because the slope has now been modified.
But the warping, what we are doing is to the magnitude response. Right?
No, it's to the entire. It's just to the values on the z-plane, right? We're just changing where on the z-plane these values line up, and so the magnitudes are the same and the phases are the same. It's just that the frequencies at which they occur are different. That's the whole notion of this, plane mapping business. That it's a one-to-one mapping of every point on the z-plane, and so whatever the properties were at that point on the original plane, you get the same properties in the mapped plane. Okay. Okay, so let's just finish up here with another design example, just to get the idea of how we're going through this. So now the specification is for a bandpass filter. And, interestingly, the specification is now in terms of hertz, in terms of continuous time frequencies, but they're specifying that the sample rate, they're telling us what the sample rate is, and we assume that there's anti-aliasing, so if the sample rate is 8 kilohertz, we assume that the analog signal was low-pass filtered at 4 kilohertz, so that when we sampled it, we didn't have any aliases, we just have the 0 to 4 kilohertz range corresponding to 0 to pi radians per sample. Here's our ripple, stop band attenuation, and we're told to use an 8th order filter with the best transition band, which means that we want ripples, if we're trying to minimize the transition band, then we're going to allow ourselves to have ripples in both pass band and stop band, so we're looking at an elliptical filter. From high level, the design path is to pre-warp the frequency specification into the analog design domain, design an analog prototype, which is always a low-pass filter, do the transformation to get the low-pass into bandpass, and so we're going to have to, when we do this pre-warping, we're going to have to figure out exactly where do we want the low-pass bandpass, low-pass passband edge to be, such that when we do the mapping from the low-pass to the bandpass in the analog domain, it's going to give us the right bandpass edges so that we get this bandpass filter when we... It's complicated, but we could presumably do it. Then we take that, generate the analog bandpass filter, and then map it to the discrete time using the bilinear transform. Interestingly, the discrete time frequency characteristics were specified in terms of hertz, continuous time frequencies, and a sampling rate. Let's just this may come up in, if you actually start doing the stuff in the projects, you may have to care about this. So the actual specification was that we wanted 800 to 1600 hertz when the sampling rate was 8 kilohertz. So 800 hertz is 1/10 of the sampling rate, which means that it would take 10 samples to complete one cycle of 800 hertz, right? Which means that we complete 2 pi radians in 10 cycles. So in one cycle, we complete 2 pi radians in 10 samples. So in one sample, we complete 0.2 radians. That basically that's unlike, we've already seen one mapping between little omega and big omega, which is the bilinear one. But the normal one we use is just when we do sampling, where we have, we have some frequency big omega here, and then it maps onto little omega, where in big omega domain, the sampling rate, Fs, turns into 2 pi radians per sample, right? And so the actual Nyquist rate, Fs on 2, turns into pi radians per sample. And so if we're told that this is 8,000 hertz, and we're trying to find the correct discrete time frequency for 800 hertz down here, then it's just, it's actually just Fp on Fs times 2 pi, right? So that's what that mapping gives you. But it's just proportional, where the proportionality is given by sampling rate. So now we get these. We can get the 800 and 1600 work out to be 0.2 and 0.4 pi radians per sample. And when we do the inverse bilinear pre-warping, we get these frequencies, radians per second, which of course are not at all these frequencies, radians per second. They're different. They're just in this design domain. That's the. We end up with totally different values here, right? 0.3 radians per second is like a tenth of a cycle of every second, so it's like 0.1 hertz. But actually, the bandpass we started with is 800 hertz. And then 0.7 is like 2.5 times, no, it's like 2.3 times 0.32, whereas here, the actual higher bandpass was 2 times. So they're not even proportional anymore because of the nonlinear warping. Sorry?
What's the big omega L?
Big omega L is the analog frequency that we're going to use to design the analog filter, which is just, we put it through the inverse of the frequency warping that's going to happen when we apply the bilinear transform, just so we can design a filter that will give us the right thing when we actually map it. You'll have noticed that I've sort of been a little vague here. We haven't gone through the steps in great detail, because of course we never really have to do this. It's all very mechanical. It's all just a question of tracking these things and doing your accounting right. And so in practice, what we do is we use MATLAB. MATLAB has this function that has all that stuff worked out for us. And it even does the bilinear transform. So in practice, if you want to design an elliptical bandpass filter, discrete time filter, you just use ellip. You give it the order of the filter that you want, the passband ripple in dB, the minimum stop band attenuation in dB, and then the frequency edges. And in fact, even if you give it one frequency edge, it assumes you mean a low-pass filter. If you give it 2 frequency edges, so a vector of 2 values, then it says, oh, you must mean a bandpass filter because you've given me 2 edges here. And then here, they're actually specified as normalized to be between 0 and 1, where 1 is the Nyquist rate. So here we just divide the original frequency is 800, 1600 hertz by the Nyquist rate, which is 4000 hertz, the sampling rate on 2, to get 0.1 and 0.2. MATLAB lets us use cycles per sample, or half cycles per sample rather than radians per sample, just because they're more natural numbers to deal with, and we get what we want. Here's this discrete time filter. It's got ripples in the stop band, ripples in the pass band. It's a bandpass filter. It's got these edges at 0.2 and 0.4 times pi radians per sample. And that's the filter that we wanted. But, we could have done this on slide 2, and we could have saved ourselves a lot of discussion. But I think it's important to understand exactly all the steps that MATLAB is going through when it does this, which is, literally doing that warping, doing the analog design, mapping the analog low-pass to a bandpass filter. By the way, the analog low-pass filter has to be fourth order, because when we change it into bandpass, we do this sort of doubling to get the sort of one image of the low-pass response here and one image of the low-pass response here. So we get this doubling of the order, and then we do the transformation to get the discrete time filter out. Yeah?
Do all the filter functions in MATLAB do it too, like butter?
Yes. All the MATLAB filter functions will do this. Oh, and by the way, we used a lip to design a analog domain filter, but we had an extra final argument, which is quote S quote, which just says, oh no, don't do the bilinear transform. The assumption is that by default, you also want to do the bilinear transform as well, so that if you don't say anything, it automatically maps it into the discrete time domain for you. Okay, so that's the story for IAR filter design, and this is something I do. This is actually useful, and these are great filters. These are incredible for an 8th order filter to have this kind of transition bands. It's pretty nice.
See that for an exam when you have to.
Well, so how does this translate into exam questions? The exam question, firstly, I don't want you to use MATLAB. Although that would be an interesting exam, right? To say, okay, can you actually do this? If I give you MATLAB, can you solve this problem? That would not be unreasonable, but I guess it's just historically it would be impractical to make sure everyone had access to MATLAB. We could probably do it now, but we don't need to do it. And we know what happens when you do this. I could ask you in the exam what would be the MATLAB command to do this. The question would not, and if I did that, I've never done that, the question would not be, do you know the syntax? Because, who cares? But do you understand what numbers you'd have to calculate to specify this for MATLAB, for some computational design system to work it out? And that seems reasonable, because that's the level of understanding I want you to get, which is conceptually, what do I need to do, and what is available? What are the tools going to be able to do? Because that's the stuff you need to understand. But more likely, the way that these exam questions work out, the ones I'm fond of setting are, I'll give you a plot like this, and I'll ask you, where did this come from? How did we end up with this? And what I'm looking for you to say is, well, what would have happened there would have been a low-pass prototype in a continuous time domain, and then it would have been mapped up, and then it would have been bilinear transformed. Okay. So actually that took a little longer than I was hoping, but I guess we had an interesting discussion in between time. Now, what we actually are supposed to be discussing now is the second half of this, the second set of practical filter design tools, which is for our second big class of filters, FIR filters, finite impulse response filters. And as we'll see, these lead us to a very different set of design procedures. We'll start off talking about the idea of windowing an impulse response, taking an ideal impulse response and just applying a window so it becomes finite length, which then turns out that rectangular windows are not the only ones we could use. There are other windows that have 0 over some range but non-zero over another range, which can have different properties. And then we'll get on to the actual practical technique, which is simply to have this thing we touched on briefly before, some kind of iterative procedure to try and optimize the approximation to the filter that we want, the ideal filter that we want, optimizing whatever parameters we want. And that's actually a very practical thing to do. Okay, so FIR filters means that their finite impulse response means we can write down the impulse response. We can describe this filter by the 15 values, which are what you'd get out of the system if you just put an impulse in, which means that the rational polynomial representation actually only has a numerator. The denominator is just 1, so it disappears, which means the system has no poles because there are no roots to the denominator, but it does have zeros, which are the roots of the numerator of that polynomial. This is something that there was no way to do this. No one had figured out a way to build these prior to the advent of discrete time systems. Now, actually, you can build sampled systems without using computers. You can have things like, these capacitor bucket brigade delays. And so there are ways you can do something like this in analog, but it was never something that was investigated because it didn't seem like a useful thing to do. So this is something that's kind of novel in DSP. And then we'll look at two ways of doing it: windowing the impulse ideal responses or the iterative computer-aided design. So if we're trying to build something like this, again, we have to specify what we're trying to optimize. It would be nice if we can say, well, here's exactly the thing we'd like to get. Here's the property we want. Now, can I find the absolute best example within my design space that achieves these properties? But obviously, the answer is going to depend a lot on what it is you're asking for. So the natural, the thing, if we say, OK, I've got this curve I'm trying to fit, which may be a magnitude response. I want to get the best approximation to it. The most common definition of best is the squared error. Or, you could have the absolute error, but squared error has algebra, just works better with calculus. If we've got something where we're trying to approximate a function of a continuous variable, then we can talk about the integral squared error. So basically this, right? We've got a desired frequency response, which we're going to define as an h of eta j omega, h desired of eta j omega. We've got an actual frequency response, h sub t of eta j omega. We're going to find the difference between them, square that so it's always a positive value, and then integrate that over all the frequencies we care about, which, because it's discrete time, so from minus pi to pi is basically all the frequencies that matter. We could normalize it so it becomes a per frequency unit, and then we could call that phi as the integral squared error. Of course, if we've got a finite impulse response, a system is defined by its impulse response, then this ht of eta j omega is just the dTft of that impulse response, which is something we can calculate, or we can write down in closed form. Similarly, if we've got a desired frequency response, hd of eta j omega, we can figure out the impulse response of that system. If we've got this fully specified, we can just take the I dTft, and that'll give us some function for h sub d of n. But unless we've sort of taken some care, in general, the I dTft of an arbitrary function, if we just drawn something, there's no reason why it should be finite length. It usually be infinite extent. Now we're trying to minimize the squared. We're trying to minimize this integral, which is basically this is a function of omega, right? It's a function in the frequency domain. Now Parsifal's relation said, well, if you have the squared magnitude of something in the frequency domain, it's actually the same as the squared magnitude of it in the time domain, modulo some scaling constants. And this, in the frequency domain, this is the squared magnitude of the difference between the implemented system and the ideal system. We've described them in the frequency domain, but it would be the same if we described them in the time domain. So it'd be the squared difference between the ideal impulse response and the actual impulse response. But we're assuming that the actual impulse response has a finite length, so it only exists for some range of values of m. So we can break this summation into the part where h sub t of n is non-zero, and so it'll be the difference between hd for those n values and ht, that squared. And then we can also have this range of values here where ht is 0 anyway, so it's just the squared values of hd of n. Right? So we get this ideal impulse response. We have our thing we're trying to set And then we have this expression for what we're trying to optimize, where it has some values involving the parts that we can change and some values that don't matter at all. So it's clear that it doesn't matter what we do with h of t, this part is not going to, we're not going to be able to affect this. This is just like irreducible error out here. But this part, well, we can do pretty well. If we just make h of t equal to h of d for all these values of n where h of t is non-zero, we can make this part equal to 0. So it's obvious how to optimize this, which is simply to take the values of the ideal impulse response, the IDTFT of the desired frequency response, and keep as many of those as we can cover with our finite impulse response and use those. Yeah.
Compute ht of n.
Yeah.
Do we need any initial value in order to start with to close this comparison operation? Like basically, we need to constantly compare ht of n and ht of n.
We need to do it we're trying to minimize this expression.
Now, how do we compute that ht of n in the first place?
We can compute ht of n. We don't, hd of n is assumed given,
No,
right?
ht.
I know, but we're assuming that hd of n is specified. That's what we're trying to match. So to try and minimize this, there's no derivatives or hill climbing here. It's just like, oh, I can minimize this just by making these two equal. If I make ht of n equal to hd of n for each value of n, then I've got this thing set to 0, so I'm already at my optimum.
I mean, like, say the coefficients for that FIR filter, let's say, if you're taking n FIR filter,
Yeah.
those n coefficients of ht of n.
Yeah.
So how do we get those coefficients first?
We just take hd of n and take those values from hd of n. Let me show you the next slide. So I'm saying that if we've got some ideal desired frequency response, HD, then we can calculate its IDTFT by using the IDTFT equation here. And for, let's say, for an HD, which is an ideal brick wall filter, we calculated that, and it looks like this sinc function, right? And we just set ht of n equal to those values for the ranges of values of n where we're allowing ht of n to be non-zero, and then ht of n has to be 0 elsewhere. But we just take the values of the inverse DTFT of the desired frequency response, and that we keep those. And then typically, we could actually take it. One thing I didn't allow myself to do here is I assumed that I was going to keep these sets of values, right? So I've got two n+1 points here, and I assume that they're symmetrically around 0. If I had the option to choose any set of points, I could sort of choose I'd want to choose this to be the set of points of HD that have the largest magnitude, so that when I null those out by matching them with HT, I eliminate as much as possible of this total squared integral impulse response. But normally that is the values around 0, because typically an impulse response will have, most of its energy concentrated around 0. So here we've just taken this chunk in the middle here, and then we've set all the values outside of here to 0. You see? I mean, you're trying to think of something which is a more difficult problem. But right now we've got a very simple problem to deal with, because we're just trying to minimize the squared error. So here is this actual instance where we've got this, we did this before, where we said, well, why don't we just build this filter with this ideal response, got zero phase modification, and then it just keeps all the frequencies in a range and then removes all the ones outside of a range. And then we know we went through the process of figuring out what the impulse response of that would be, which is just this sinc function. The sinc function goes on forever, so we can't exactly implement it in a finite number of points, but we can get the best finite length approximation, which is simply to take the middle points here. Just take as many as we can cover, and then forget about it beyond that, set it to 0. And we've just proven that that's going to give us the least integral squared error approximation, the best approximation in terms of integral squared error for the frequency response. And so here, to make it into a causal response, we can just delay it by m points if we've got a 2n plus 1 point filter. And so here's our nice finite length approximation to an ideal low-pass filter. So what is the nature of the approximation? We know that it's not going to be exactly the filter response we ask for because we truncated it. We know that there's going to be some impact of that truncation. We can take the Fourier transform of the finite length filter and see what we got. And this is what we get. So we're trying to build a filter with a response like this that was 1 up into 0.3 pi in this case, and then 0 beyond that. And then what we're doing is just taking some truncation of that. And so here's the result of taking the middle 25 points of that sinc function, and here's the result of taking the middle 129 points sinc function. I'm taking odd numbers because it's going to be symmetric around some central point. So by taking an odd number, I preserve its symmetry. You can see that as we go to higher order filters, we get a better approximation. We're trying to minimize the integral squared error, which is, the sort of the size of these lobes and this triangle of error in here. And you can see that here, there's a lot of error in this lobe here. In this higher order thing, these ripples are staying smaller magnitude, and there's still this big lobe here, but it's much shorter, so its integral is less. And the blue curve does look closer to being like this rectangular step. But what we didn't do was reduce the peak deviation. That actually the peak deviation of these two is more or less the same. It's about 9%, it's about 1.09 up here. All that happened was we took these ripples and we sort of squeezed them in so that their integral was lower, but their peak error was more or less the same. And this is called Gibbs phenomenon, and these things are sometimes called Gibbs ears because they're like these little things that stick out around the side of a transition or a feature in your frequency response. And this is kind of a problem because, well, we started out by trying to optimize integral squared error because that is the thing we can do very easily. But up until now, when we've been designing filters, what we've really tended to say is like, well, okay, I can't have an ideal filter, so I'll get the filter that has the least worst case deviation. I'm trying to minimize the maximum deviation away from the desired frequency response. And in this case, changing the order of the filter hasn't changed the worst case deviation at all. It stays the same. And that's the problem that with this truncation approach, I don't control the worst case. I'm not optimizing the worst case error. I'm just optimizing the integral squared error because that's what I set out to do. So that's a problem. When you look at this, it's like, that's kind of weird. What's going on here? Why are we getting these ripples? It seems a bit mysterious. But it's actually something that we can understand quite easily if we think about what's really going on. So what we did was we took HD of n and then we truncated it to be 2n plus 1 points. That truncation is basically the same as taking this infinite length signal and then multiplying it by a window, which is 1 over the points that we kept and 0 for all the points that we dropped. And so here's our original HD of n. Here's our rectangular window, WR of n. And the product of those two, multiplying them in the time domain, gives us the actual HT of n, the finite number of non-zero values that we implemented as the impulse response of our FIR approximation. Multiplication in the time domain is a dual with convolution in the frequency domain, right? Just like convolution in the time domain is a dual with multiplication in the frequency domain. So this product of the ideal response and the windowing function has a Fourier transform, which is just the convolution of their two frequency responses. And so we can actually, what that's saying is we've got this ideal response here, which has got this sort of brick wall behavior. Then we've got the rectangular window that we multiplied it with. The Fourier transform rectangular window is this periodic sinc, this sort of thing that looks like a sinc function over the range minus pi to pi. And so that's what we're sort of sliding over here to get our result. And then it's like, oh, okay, that looks about right. That if I take something, if I take the convolution of two things like this is kind of the result that I expect to get with these ripples, which are basically the partial overlap between these two functions. Let me just, so I put together an animation in MATLAB to try and illustrate where that comes from, which I just want to show you now. In fact, no, I put it together in MATLAB and then I converted it into a movie so we can just look at the movie here. So what this is here's the ideal frequency response, the step function. Here's the Fourier transform of the rectangular window in time. And what we're saying is the actual effect, the resulting frequency response is the convolution of these two things. So I'm thinking about convolution as this idea of sliding the two functions relative to each other and taking the inner product, multiplying them together point for point and summing it up. And so as we sort of step through this, what happens is the nothing. Yeah, it was so much better in rehearsal. Let's try that again. Okay, here we go. Now I'm sliding these two, and then what I'm plotting down here is that inner product of the overlapping parts. So to get this point here, I multiply these two functions together. Out here, the blue function is 0, so I get nothing. So all I'm getting is the sum of all these points from the red function, right? The parts of the red function that fall inside this block in the blue function, I sum them up and I get some point here. And so you see this thing ripples around here because, like, you know, whether the largest point here is, you know, the bigger points here, where they're sort of averaging out to around 0, but whether you actually include a lobe or not will give you little ripples here. When it gets interesting is when this large main lobe of the sinc function starts falling into the blue portion, and that's when we get our transition to the pass band, right? So now, sort of, we've got half of this big main lobe in here, so we're sort of halfway up, and we keep sliding in, and once we've got all of the main lobe in here, suddenly our magnitude response has gone up to be something large, because now we're including this big chunk in there. But, you know, we have these relatively large negative side lobes, so once we include both of those, then we get a minimum here in the magnitude response, and so on. And then once the big main lobe slides out, we get the magnitude response going down. So this is visibly, this is what we got. This is our Gibbs ear type response. And you can sort of see how it comes out of this convolution between this ideal response and this thing. And moreover, you can see that the things that are going to really determine these properties are to do with how wide this central lobe is and how large these flanking side lobes are, because the width of the central lobe is how long it takes to get from here to here, the transition width of this frequency response. And then the size of these lobes are the things that give us these large Gibbs ears, these large ringing artifacts around the edge of the transition. So that gives us this idea that we've got a window here, which is what we're multiplying by. Let me just finish this off. Give me a couple of minutes. We've got this window where we're trying to multiply in the time domain, which is convolution in the frequency domain. The window has some kind of main lobe width. It has some kind of side lobe height. And those parameters give us the transition band. The main lobe width gives us the transition band. And the side lobe height gives us the ripples. The main lobe width for a rectangular window is inversely proportional to its length, right? The longer it gets, the more compressed in these sync ripples get. And so the shorter the transition band gets. And that's what we saw when we used the 129-point filter, which is, you know, multiplying by a 129-point rectangular window. We had these narrow ripples in the rapid transition band. But the side lobe height, which comes from these first side lobes, they don't change very much when we change the length of the rectangular window. They just get squeezed in, but the maximum deviation stays the same. However, rectangular window is not the only window we can use. We can think about some other different kinds of shapes which have different Fourier transforms with different main lobes and side lobe heights, and that's how we can get different kinds of of windowed filters. So we'll talk about that next time, but I just wanted to set that idea up for you. Any questions? Okay, see you on Monday.